Okay. Don't everyone all speak at once.
I did nothing this week on Casper.
What's that? I couldn't hear.
Did nothing this week on Casper.
Okay. Well, actually, I think that the ladle work is is actually very Casper related, especially for our implementation. And
we did a whole bunch of work on K-framework. So if we intend to implement Casper as a K-framework transformation, then that's relevant.
Yeah.
Yeah, actually, I met Everett this week.
It sounds like Vlad is speaking, but it is very nearly muted.
Hello, how's this?
Much better.
Okay, so I met Everett from.
No, you changed it again and can't hear you.
All right, how is this?
That's good.
Okay, yeah. So I met Everett from K-framework this week, and I was thinking, like, I don't think we necessarily want to implement Casper as in K-framework. What I think would be really cool, though, it would be to replicate reduction system that's, or maybe crazy version is, have like a K-framework interpreter for a smart contract environment.
Yeah, that might be a little bit slow, but for sure, you can certainly use the information associated with a rewrite system as input to something that will provide a. Sorry, there's some kind of weird rustling. As input that will provide a replicated version of that. So you can imagine enhancing K-framework so that it provided an auto-generated replicated form of the rewrite system that's synthesized from the input.
You mean?
Oh.
Okay. Yes. Do you hear me okay?
I can hear you now.
Sorry, we're struggling with various phones and speakers and stuff. So do you mean like that we could replicate a system that's specified in K-framework?
That's correct. So
that's also kind of what I was thinking.
Yeah, that makes a lot of sense to me.
But also, I think one really cool idea is that, like, rather than say specify a particular rewrite system that we want to replicate, just like say, hey, look, specify your own rewrite system, and the blockchain will replicate that.
Well, that's what I was saying. So what K-framework is providing is the mechanism by which you specify a particular rewrite system. And so imagine that you provide the syntax and the configuration, the rewrite rules. That's all K-framework related, and K-framework can provide the means by which it's parsed, and some version of it is run. But then there's an enhanced version of K-framework which would then replicate that thing. Right. That's the part.
Yes. Right. And so kind of the difference between that and what I was saying is that, like, it would be really cool in some way if you could like submit a transaction which says, hey, look, here's a new computational system like this, and like introduce it to the blockchain. Then have it kind of like know and understand that.
Yes. Yeah.
That's cool. Kind of like a higher level idea. It's kind of a, it's a way that we can potentially cop out of deciding like what the rules of the EVM should be. Or just say, hey, look, here's a language for specifying all possible EVMs, and so.
Right. That's what I was saying. I think we're saying the same thing, to be honest. So all I'm saying is, you've got to be able to write down a particular rewrite system, and K-framework provides one means to write that down. Once you have one written down, then you want to be able to replicate it.
Right. So that's pretty much what I'm saying. Yeah. But I want to do it not just like kind of on a case by case basis, but on the fly. Like I want in some way, like this is kind of, a little bit far removed from today's realities, but somehow it'd be really cool if we could just like on the fly be able to specify new a new computational system that the blockchain could replicate without having to deploy a new one just for that one.
Yeah. Cool. Oh, I think that might be fun. The on the fly stuff in general is good for prototyping, not necessarily good for production systems. But I get your point. But with that in mind, Mike and I have been looking at a little more detail at how one would write down even just a toy version of Rho in K framework, and we made some progress on that front.
I saw Everett go through like the higher level language that he wrote for the EVM on the back of his K framework implementation of the EVM, and it was so cool the ease at which he was able to do that.
Yeah, exactly. Now we're starting. That's the point. You can see the payoff of writing at this level of abstraction.
I mean, he had like a kind of correct, like a pretty much correct by construction higher language for like a restricted subset of the EVM that he put together in a few days.
That's exactly the situation.
And it was like really nice looking language. Also, it was not an unsightly thing.
Yeah, that is precisely the point of working at this higher level of abstraction. And what it does is it suggests that a lot of what we're currently seeing as the value of the platform is all commoditized. Anybody with a few days worth of effort can put together something, and then with a few months of effort can make it considerably closer to production. As opposed to the kind of capitalization that it takes right now to build out a blockchain-based platform. So that's the thing that's really exciting to me is because it really significantly pushes the value proposition over to the applications and less to the platform. So all that's, from the platform point of view, once you have a robust family of Casper algorithms that work in a namespaced or sharded kind of way, and
is our rewrite proofs sharded in the way that you want?
For the class of languages that we've got, yes. You have to build it. You have to build it into the theory. So it's not.
So if the theory is sequential, then you're never going to get it. But if the theory is not sequential, then do you get it for free?
No, it's not about sequentiality. It's about the first classness of locations at which transactions take place. So
that sounds interesting. You want to tell more?
Yeah. So it's the whole reflective part of the Rho calculus. It's the fact that the Rho calculus names have structure. So you don't. You don't really get this for free in the Pi calculus, right? You get some notion of this, but without some sense that the names themselves have structure. You can't do any sort of analysis on when you're going to have contention, except by looking at whole programs.
Could you maybe do that analysis by looking at like types on programs?
You can do some of it, right? So there's this whole thing that was kicked off by Mads Tofte in the late 90s and early 2000s called region analysis, which is type based, and this is closely connected with the language based security stuff. That's also type based, but it ends up, as I said before, it ends up being more computationally intensive. So you have to do whole program analysis. And what you want to be able to do is to combine the two techniques. So you can do both whole program analysis and name or location-based analysis, right?
Okay.
And so the two make it feasible. And that's what's
That sounds interesting. That sounds interesting. So somehow, this seems to apply really well on the level of reductions, but we might have it in the end that a block is allowed to do up to 1 million reductions, and and has these things called transactions, or maybe let's just say like a block is a set of 1 million transactions or 1 million reductions. Then is it easy to aggregate these pictures and be able to compare them on a blockwise basis if you just have like a kind of collection of reductions?
Yeah, I mean, I don't know. I mean, you've seen the proposal that I made like over a year ago now, where instead of aggregating instead of doing it on the basis of number, you do it on the basis of the shape of the transactions, right? So think about the one way I've been trying to explain the idea is think about it as programmable blocks. So the blocks say what gets in and what gets out on the basis of the shape. And then the only time you ever have to run Casper is if there's any sort of disconnect between a couple of programs that say what gets in and what gets out. Right. So think about the validators as proposing rule sets for blocks. And those rule sets are effective. You can think of them as compression. Right. So if you expand the rules, you generate the set of transactions that are permitted in the blocks. And then the only time you ever have to worry about conflict is you worry about conflict if the two rule sets are in contradiction. And so then what you're looking at is to find a way that to provide sort of the maximally consistent set of rules that are going to generate the blocks.
Yeah. So at the moment, the kind of the fork choice mechanic actually does end up taking care of the kind of the first thing that you were after, which is the idea that we won't need to make a decision if they're not in contention. I'm not sure actually if we need to explicitly I don't know. So I guess what do you think will reasoning about it, like these kind of inconsistent rules give us that like the fork choice kind of thing doesn't? And the fork choice rule, basically, what it does, it kind of only creates the mechanic is basically that there's only a fork when there's contention. If there's no contention, there's no forks.
Yeah, that's good. That's a good way to think about it. So the first question is, how do you detect contention? And the second point is not having to worry about size. So the rule sets say, I don't really care about the block size. What I care about is the program that says what blocks are in and what blocks are out. And then,
but that like program might not be, might not actually restrict the blocks that much because of, or does it have to, or if it does, it's better. I'm really hoping that economics is what restricts the size at that point, right? So think about it. Think about it in terms of just the way normal systems. That's really cool. I mean, you just compensate people for more like for giving tighter descriptions on what's in their block. That's exactly right. And think about it like this, right? Think about like cron jobs or other kind of batch systems, where they're all about being able to describe jobs on the basis of things like, well, we need all the jobs that ran before 5 a.m. or all the jobs in the Southwest Pacific data center region that ran after 9 p.m. Right. So the point of the rules is to be able to describe things at this higher level, and then those are what gets in, and then you have the economics that. Ideally, we'd have stuff like, oh, look, I'm making blocks for this application, and then people who are making who want to who aren't using that application maybe, or people who are using another application will know whether their application is ever in contention with that one, and therefore can maybe never ever talk to you. Yeah,
Exactly. So
that sounds really cool, but also sounds like you need to restrict the language of these descriptions in order to efficiently do contention detection.
Yeah. Well, I mean, in general, you have to restrict the language so that you can, you don't want it to be a Turing complete programming language for the rules for the blocks. It's going to be a much smaller, simpler language that where the decidability comes down to the decidability of type checking of the transactions against the types that are the rules for the blocks. That
sounds like everything we need.
Well, anyway, that's kind of the architecture that we've been pursuing for a while. So Mike and I did a little deeper dive on K-framework. And Mike, did you want to show the two little toy things for Rho?
Yeah, so we had described two different reflective combinator calculi. One of them based on Yoshida's combinators, which she got by an abstraction elimination process on input names. And the other one using SKI to eliminate input names. So
sorry, can you repeat that real quick?
Right. So PyCalculus has two sources of new names. One is the input prefix, where you say, for a message Y read from a channel X, Y is then bound. It introduces this new name Y for the process, the continuation that follows. The other is the new name. And so if you say new X in this process, X is just a new channel. So there have been various attempts at eliminating bound names. In the lambda calculus, there's this classical result from Schoenfinkel and Curry back in the 30s that you can eliminate the bound names by using these things called combinators, which are denoted S, K, and I. And in this language, I've got them right here. The rules are that when you apply I to X, you get back X itself. So I is the identity. K is for constant. If we have constant applied to X and then we apply that to Y, it returns X. And then S, I don't know what the original mnemonic was, but for me, it helps to think of it as sharing, that it shares Z with X and Y. So here it passes Z to X, and here it passes Z to Y. And using these, you can write down any lambda term as a bunch of SKIs applied to each other.
But can you write down naming or binding, variable binding? Does it somehow encode this?
This removes the necessity for bound variables.
But it doesn't.
Lambda calculus.
Not by defining them, just by saying, "Hey, look, something else. There's equivalent. This is other equivalent thing."
You can implement lambda abstraction and application using these things. So if you think of lambda abstraction as the lambda abstraction together with application and substitution as the core mechanism of naming, at least as regards to programming language semantics, then yes, this provides a mechanism by which that can be realized.
Yeah. So instead of having a beta reduction rule,
quick kind of like high philosophy question, like, if in terms of like Curry Howard or something, if I can implement program 2 kind of in program 1 somehow, or implement language 1 in language 2, and does that mean that I can define everything language 1 in terms of types in language 2, in terms of the formulae in language 2? Like, is there some kind of relationship I was talking about the definition, and then you're talking about an implementation, and somehow I'm trying to see if there's like a nice mapping, like, somehow it seems like a definition, it may be a constructivist definition is an implementation or something.
In order to have the kind of type level correspondence that you're talking about, there has to be a faithfulness of the translation. So, and the gold standard for the faithfulness of translations is that whenever two programs are equivalent in language 1, that happens if and only if their translations in language 2 are also equivalent. So that's called full abstraction. And so whenever you have a fully abstract interpretation, then you get that kind of type level correspondence. But the main thing is what Mike is talking about. It doesn't require that you have a that level of fidelity between the two. All that's being said here, and this is what Curry and Schoenfinkel were talking about, was, what if you felt like the lambda calculus was magical? And a lot of people back then did, right? A lot of people thought that the existence of the Y Combinator made the lambda calculus be suspicious. They thought, there's probably an inconsistency here somewhere. So you take the S, K, and I, and the rules are really, really simple, right? I mean, Mike has them highlighted there. That's how simple they are. And then you can say, well, everything that you've got inside the lambda calculus, we can do here. And if you think of the lambda calculus as a theory of naming, right, a theory of substitution, then this provides that. You can realize all of your substitution magic here, and so this made it considerably less mysterious.
And does this do anything more than lambda calculus?
No, because each of these can be expressed as a particular lambda calculus term that's small.
Great. Great.
So anyway, Curry and Schoenfinkel did this abstraction elimination ages ago. Then, much more recently, after pi calculus was introduced in the 90s, Yoshida tried to do something similar for pi calculus. And in Yoshida's combinators are denoted here, along with M, but most of them are here. She was able to get rid of binding that came from input, but not from new. So if you look at her paper, you'll still see new appearing in her translations, but you won't see any input prefixes. Now, Greg, along with Matthias Radestock, figured out how to eliminate new by using reflection. And so in these two combinator calculi, we've done the same thing. Instead of only using names, M here is for message. We can now output a term or a process as the second parameter. And in the original one I was showing, ski row, in addition to the SKI combinators, this is much more close to the pi calculus or row calculus that Greg has. We have these in and out prefaces. We have quoting and dereference operators as well. So this is the entirety of the rule set for this row combinator calculus. And I can say here, this part is this part. This says output right there. This is the identity. Use the Y that is being passed in at this point. It says dereference. That's the identity. So the S distributes Y over both of these. The S then distributes Y over both of these. K out drops the Y and just returns out. I returns Y. So this says output Y. K star drops the Y and outputs star. I outputs Y. So this inner part here is the encoding that uses no binding in order to put Y in the right spot in this expression. But it also has the par rule that says if I par two terms together, it splits it up into two separate terms, separate processes running at the same time. This says if we have an in and an out running on the same quoted process, then they synchronize, and the continuation gets whatever was sent over here as a name to be used here. In this particular implementation, just for convenience, I also allow identifiers as well as quoted names, but in the real one, we'd get rid of that. In the Yoshida version, I also have identifiers just for convenience, but each combinator here has a different interpretation. It says if you have a distribute combinator and a message coming in on the same channel A,
Sorry.
Was that comment for us or somebody else?
I think it was somebody else.
Okay. So D is for distribute. It takes this process P and distributes it to B and C. K is constant. In this case, it just drops it. Forward, branch right, branch left. You can see that at P goes forward on the right and on the left here. S here does not mean the same thing as S in.
No, it's sequentialization.
Yeah, this takes these two and then sets up a forwarder between them. And finally, this is dereferencing. So if you get a message in, you dereference it and it becomes P. So if we wanted to, we could right now implement row-lang in terms of these, and we'd have a K-framework implementation of it. The problem that we're running into at the moment for implementing row calculus directly in K-framework is that the substitution package isn't aware of at as preventing binding inside of it. So we need to be able to say, you can substitute terms outside of this, but you can't substitute underneath an at sign. So, but other than that, we can do all of row calculus. So that's what I've worked a lot on this week.
That's really cool. So the new I thought, don't you guys have combinators for getting rid of new?
That's the quote and dereference that allow you to do the trick described in Greg and Matthias' paper.
Oh, okay. So there's two sources of names, right? One is abstraction, which is gotten rid of via SKI, right? And the other is new, and that's gotten rid of by reflection.
Okay, somehow I missed that. I missed that. That's really cool. That's really helpful.
And you did an implementation of something. You sent me a nice picture, a nice JPEG.
It's a GIF.
Yeah, a GIF. Sorry, a GIF. Yeah.
No worries. Yeah, I mean, if you want to go to my part of the update, we can totally talk about that.
Yeah, please. It's already 40 minutes in, I'd like to hear about that.
Okay, cool. Yeah, I lost track of the time, I guess. So basically, we have there's IC3 boot camp. This event where there were like 10 teams that like kind of hacked on various Ethereum projects, or somehow Ethereum related projects. I kind of like broke off and worked on just implementing the blockchain replication, which basically is this algorithm that I described, I think last stand up or maybe the one before, where I have like this ghost fork choice rule, and we could totally kind of go over some code real quick and look at these GIFs.
Sure. I just want to make sure I take a little bit of time to show some really cool progress on Rolang. But yeah, go ahead.
You want to go code?
Yeah. Should we share
screen? Just pulling. Well, yeah, screen share. Cool. So basically, we have like this fork choice thing, which kind of this is kind of the kind of relevant code in some way. This kind of implements Ghost in some way. Basically, it starts off with the last finalized block, and then it goes through the children of that block, which are held in this kind of reverse pointer map children. And it kind of picks out of the children the one that has the most weight, according to the latest messages out of the children on top of this block that we're working on currently. And so we start off with the last finalized block, and then we pick the best children based on the weights according to the latest messages. And then basically, so if someone's latest message is on one chain, then we'll be able to kind of like tell whether that child is in that chain, actually. So whether the child is part of the blockchain that the latest message from a particular validator is on. And if the validator is on the same chain as that child, then that child gets their weight.
So this is Python.
This is Python, yeah. Okay. So we have this kind of while loop where we're going to get the best block of the child. This could have been a little recursive function, but it's a while loop. And here in block.py, we've got like the thing for checking actually if it's in the same blockchain. And this guy did make a recursive guy. And so basically, self equals block, then true, block that is none, then false, and then you just kind of recursively call yourself with it's a block function that calls itself with a block also. And so somehow it checks if one block is in the blockchain of another by going and looking at the parents of that other block until Genesis. Not the most efficient code, but that's kind of the thing that's checking if in our fork choice rule, if whether we should add the weight to their of the weight of the validator with that latest message to the child. And this is in the get favorite child bit. Mm-hmm. So there's a bunch of children, and we just like add their scores if they're in that blockchain. In the blockchain given by the latest bets. And so that should be like, it more or less clear, but it's especially clear if we run it or if we look at the GIF. Can we run it, Carl?
You
might have to pull.
Yeah, I may have to pull.
You just pull, it's fine. Just try running it.
Okay.
Python, Casper.
Yeah, okay, so I have to make a virtual environment and stuff, unfortunately.
Oh, okay. Well, then maybe we skip it.
Yeah, okay.
Okay, so so basically, at the end of the day, somehow I implemented. Well, there was kind of two phases. The first phase, I refactored everything that I possibly could, as far as I kind of like easily foresee, in the binary consensus to make minimum changes to make the blockchain consensus. Oh, check it out. We got ourselves a demo of the blockchain-based consensus. So check it out. We have 10 validators here. And the red one is the fork choice rule. And kind of the dotted lines are justification pointers, and the solid lines are pre-block pointers. And the fork choice rule basically is was kind of all of these blocks are considered children of none, and we kind of pick the one with the most weight and choose that one. And the one with the most weight here is this guy here. And then we have to pick, and then we go to the one with the most weight. Sorry, when we initially started, we saw one edge going out of him, right? And that was why. And now we kind of have to ask about the weights on the. Here we have like this guy's weight, and this guy's weight. So this guy's weight is on this one. And this is the only child actually of this block. And so we didn't have a choice here.
Mm-hmm.
The justification pointers can be used to prove that their fork choice rule was actually the best fork in their view. And that's kind of one of the key mechanics to make sure that block validity restricts validator behavior as much as possible. We have these pre-block pointers that, see, we had this blockchain earlier, but now it kind of forked, right? We're over here on the right now. We were here before, and now we're over here. And I'm just gonna keep running it for a little while. And now check it out. We're not even on this max weight validator anymore, because these guys managed to actually have more weight on their chain in total by passing it around between more validators, in a way that it reflected in the latest bets that we've seen, given this kind of global view. And so somehow, it's going to keep forking away. Sometimes orphaning blocks. So like this is kind of, you can think of this as an orphan block, and this is an orphan block, and this is an orphan block. Any block that didn't end up making it on the main chain is somehow orphaned by our normal definition. There's a bunch of this guy's like looks there's like a whole orphan little tree here, but this tree still may contribute, for example, with this bet here, to the latest weight of all the children on the south of this of where this remerges with this chain. And so at this point, we're gonna kind of eventually see that it like stabilizes at the bottom, but actually there's a more recent version of this, which shows also the validator's fork choice rules. Which, I mean, let's just observe it on my kind of GIF. Do you know what that is? Oh.
Yeah. Huh. Okay.
Yeah, there we go. Should be fine.
Yep.
So these kind of the blue lines are the latest fork choice rules by given by the validator's latest bets. So every validator has a fork choice that they have to make, and their pre-block pointer basically points to that choice. And so basically, I kind of started from the pre-block pointer and painted everything blue. The red is still our fork choice rule, but now from this one we see not just kind of this accumulation of pre-block pointers, which we still see here, but also the fact that people's latest estimates don't have blockchains that aren't on this kind of blockchain that we have as our fork choice rule watching the system. And so that kind of shows you that these nodes somehow know what we know, in that they're choosing the same fork choice as we are. And this is kind of something you would expect from a consensus protocol, where kind of the clients who are watching and not making messages would eventually make the same decisions as those who are actually the underlying validators. And so basically what we kind of see here is like the blockchain hardening, and we don't have yet the safety oracle, but super soon, hopefully we will. And we're going to see basically green kind of following this thing to show us that basically this thing will never be reverted. It has like finality in the traditional kind of consensus of the word, or sorry, it can be used for consensus decision with consensus safety at that point. But so we don't have finality detection, but we kind of know that we're getting finality just from, results on fewer nodes that we're able to sketch out on paper.
This is awesome.
Yeah, it's pretty cool. It kind of has a lot of the nice properties that we would kind of hope for. Namely, like all of the nice properties we would kind of hope for. Yeah. So I'm kind of excited about that. The kind of one of the more compelling things I can now kind of say is that if validators make and that's I could have probably said this before, but somehow it's not really come to my attention more kind of recently. If validators make a perfect round robin, i.e., like each validator makes N validators, each of them make one block in this round robin, and they kind of do it after they do the round robin, they will have someone who sees this will have consensus safety in the context of no Byzantine faults on the fact that the first block is going to be the block that's in the blockchain, or is definitely going to be in the blockchain in the future. And then when an additional block comes along, say like a block from another validator on top of the round robin, that will additionally provide consensus to the second block. And then like when a third block comes around, another block comes around, that will provide consensus on the third one, but also contribute to the fault tolerance of the second and the first, and the previous new block that we talked about, we would have also contributed to the fault tolerance of the first. And kind of what we kind of get by making this blockchain then is at the end we get one block contributing to N blocks in terms of security, in terms of fault tolerance, and in terms of consensus, just in an asynchronous network. And so somehow we're being like, I think. And because that can be like, if you go in the round robin, anyways, exactly the amount of their weight, that this is kind of like a theoretical optimal in terms of message efficiency, like the number of messages used per unit of fault tolerance per unit of consensus in some way. Like it really can't get better than one block contributing to the security of, every block. Basically, it's somehow increasing the fault tolerance of block of a block to a different to higher thresholds by their weight until it gets to 100%. So let me try again. So in terms of the asynchronous consensus without any fault tolerance, like there's no theoretically best we can do than getting one finalized block for every block we make at the margin. And somehow like that's also going to be the case for every fault threshold, because if you kind of have to continue the round robin enough before you get to this point where every additional block becomes pivotal on one block. So there's some latency, N if you're just looking for asynchronous safety, and N plus some number if you're looking for fault tolerance, depending on the weights of the validators. After which point you start to get this like really low cost of consensus of like one for every block. And so like that's kind of cool. And let's just kind of make this nice trade-off between like super low overhead and super low latency on finality while with higher overhead. While it's still, even in the case where we make a blockchain, getting all of the nice properties of traditional consensus protocols. Cool. Way less overhead, because every block contributes to the safety of like lots of other blocks. Somehow we kind of have a big multiplier. Normally what you do in like one of these traditional consensus protocols is you like individually finalize every step.
Right.
Which is kind of way less efficient.
Yes.
And so I'm excited to see, kind of what in a, this kind of network model or whatever, I'm able to get in terms of efficiency. Like somehow the perfect round robin is somehow optimistic. We're not going to really get that a lot of the time, and then that means we're going to have to pay a little bit higher cost in terms of overhead per consensus, per unit of consensus. And so that's kind of exciting. So I'm kind of excited just to even have this toy somewhat, because like, the blockchain consensus, once we have a safety gadget, is going to be, only like only like an incentivization and a validator rotations away from and a client away from actually being like a blockchain, like a proper public one. And B is not that far away from rewrite replication.
That's awesome. That's really, really cool. Well, speaking of which, let me just take the last 4 minutes to do a quick for Rolang, we've made some fairly significant progress. Here's the repo where folks can go see an implementation of the ERC core of the ERC20 token semantics in Rolang. It's roughly the same size. Of course, the semantics are a little different. We've added one feature to the language, which is you could think of contracts as associating a name to a process body, and that process body will be on the blockchain, whereas the defs are not necessarily, they're volatile. So again, they associate names to a process body, but the state is volatile as opposed to the contract, which is non-volatile state. So in this definition or in this contract specification, we have essentially this is the process body, and these are a bunch of local declarations here. I don't have enough time to go through all of the code. Unfortunately, we can go through that at some other point. The main point is that the message passing paradigm and the reflective paradigm seems to provide a good fit for the domain. And it's relatively straightforward to read the contract and see what it's doing. The next step, and this is part of what's going on with the K framework work, is to get the type system in, and then after that, we will be able to start writing. And by the way, this compiles to the Rosette VM and executes. So you can test it out yourself. The important thing is that I wanted to mention is that the next step is we want to start writing the Casper level contracts in Rolang. So this will test out Rolang, and it'll sort of be the next level test for Rolang, and allow us to hopefully have a lot more control. So when you think about the way our chain is going to be built, there's a layer. There's a layer with sort of not blockchainy, and then on top of that, we can define the Casper contracts, which then give us the kind of replicated persistence that we're looking for. So it's 2-level, as I've been mentioning. I don't know, for almost 2 years now. So I think this is to me, this is very encouraging. We've made a lot of progress, and once we have the Casper contracts in place with the type system, then we'll get the correctness of the implementation, the match of the implementation to the specification through the type checking, which I think has been the other part of the thing that we want. It's one thing to have a proof in a formal system, but then that proof, isn't related to the actual code that you have in production. Here, we hope to have a big chunk of the proof of the correctness represented in the fact that the code type checks. So that will be, to me, that will be very, very exciting. So any questions or comments?
I don't know. I mean, when you say contracts, like, it sounds like you're talking, like, it doesn't necessarily sound like you're talking about just smart contracts with maybe like a combination of smart contracts with validator code and, like a bunch of other things. There's like the whole consensus protocol, in some way, isn't just a smart contract. And I know that when you say contract, you generally don't mean just smart contracts. You mean something a little more broad.
Here by smart contract, what we're saying is that this is a Rolang. These are smart contracts.
Yeah, but the contracts that you're saying are going to implement the replication are not smart contracts. They're just ordinary.
They're not. They're so these are effectively just so the things that implement. Yeah, that's why I'm saying it's two levels. So the smart contracts live in the upper level. So they're smart in the sense that they reside on the blockchain, right? The contracts.
Maybe smart in the sense that they're kind of enforced. Their terms are enforced by the blockchain.
Yeah, that's another way to say it. But the main thing is just that they've been replicated, and because they've been replicated, you get all kinds of good properties for their availability and robustness. But Rolang is sort of a general purpose programming language, right? And it runs on top of a VM, and then we implement in terms of that VM the Casper level contract, the Casper level contracts, and then we provide the blockchain semantics above that. So it's like an onion, right? It's like we're replicating levels of the onion.
Okay.
That's
interesting.
This is all part of the desire to have the types for the Casper implementation provide a significant portion of the proof of correctness, right? So just the fact that the Casper contracts type check at all is the proof that the implementation matches the spec. So that's always a gap that one has when doing formal methods, right? So you write this beautiful proof in Coq or Isabelle or Hall, and then you go write production code, and that's in C or C++ or Java or something. And the relationship between the thing that you prove correct and the thing that's running in production is a bit of a mystery. It's like, well, I don't know. I hope it works.
I tried to spec.
Right. Whereas here, the idea is that the types constitute a significant portion of the spec itself. And so when the program or the contract here type checks, that provides an automated proof that the program conforms to the spec. And already we've seen that the kinds of things that we can check with the types and realistically check with the types will give us a significant level of security above what we're seeing so far in the space. I haven't had a chance to look at it in detail, but I'm fairly certain, based upon the descriptions, that the parity bug on the multi-sig would have been the kind of thing that we can catch with our type system.
Certainly. No question.
So then there would have been, that just wouldn't have been deployed, and we wouldn't have people scrambling. Anyway, that's the kind of thing that we're hoping for. And then once we have that level of security on the implementation of Casper, and we've got this sort of completely a concurrent implementation that's, it's all already automatically message passing, because that's all you can ever do in Rolang is pass messages amongst processes. Then it will also be, performant. So we'll have this, performant correct implementation. And then above that, we have a notion of contract that can utilize the persisted replication mechanism. Does that answer your question?
I mean, that's cool. I mean, I don't remember what the question was, but definitely I feel
sorry. I tried to make my answer shorter.
I mean, I'm comfortable with 2 levels of contracts, implementing like validators at higher levels, using at lower levels. The thing that I'm a little bit more uncomfortable with is like how you can do reduction across shards. Like imagine sending a message from here to there, but like I don't know what process is stuck on the other side, what it's going to be bound to on the other side. I just know that it has to go from here. Somehow it seems like it's going to have to go through an intermediary before it goes to the other shard, in order for the kind of shared intermediary, in order for like my shard to do a reduction with that, and then your shard to do a reduction with that also, so that we don't have to have each other's kind of P's and Q's or whatever.
Well, yeah. I mean, the nice thing is that the whole system functions as an uniformly. So the intermediary is just the communication mechanism that is the same between processes within a single shard. The only difference is that processes across shards use more complicated names. So think about it. Like processes within one shard are using URLs that have a shorter prefix or a longer prefix, depending on how you look at it. And processes across shards are using name URLs as names that have a longer prefix or a shorter prefix, depending on how you're looking at it, right? So it's exactly the same communication mechanism. The only thing that separates them is the fact that they're, as being in different shards, is the fact that
another thing that separates them is that, like, you kind of can't really do the reduction atomically without a cross-shard protocol. That, like, there's like, so it's not that easy to do this like a reduction that affects 2 shards to make sure that like each side are affected in the appropriate way. Like, what if the message fires and it is never received?
Right. Then you don't ever get the reduction because there's no corresponding.
You have to like unfire somehow. If you
No. That's the same. That's the same whether you're happening inside a shard or outside a shard. You might not get the message for any number of reasons.
Well, so I'm assuming that is running. I'm assuming that there's like validator assignment to shards, and like a validator can like quickly do a reduction on their own computer, but like can't really quickly and easily do it across them.
So what you do in all of those protocols where you do have an issue with respect to garbage, like you can't just wait forever, you have a timeout. So you're always racing against the timeout. And that's just standard in all of these networking protocols. If you can't wait forever, you must be racing against the clock. Right. So you don't unfire a message. You arm an alarm whenever you fire a message, right? And if one side or the other or both can't wait forever,
there's so many ways that like that it can seem like it's succeeding and then actually fail due to Byzantine faults.
But I argue that all of those same things are happening within a single shard, that they're happening across shards. Otherwise,
I'm saying cross shards. It's additionally more complicated.
Well, yeah, I think this is a great conversation to have. Let's talk about that at the next Casper. This is awesome.
Sounds good. Anyways, I think it can be boiled down to how shards do I/O, but let's talk about it later.
Yeah, for sure. Yeah.
Okay.
Cool.
Bye, everyone.